Um, we are solving for the relationship between molar diffusive flux and mass diffusive flux. Um, and this will be in terms of molar diffusive flux, mass diffusive flux, um, molecular weight, and mass fraction. So starting off here, um, we have our molar diffusive flux. We're going to get the formula for that. And the molar diffusive flux here equals concentration of A times times the velocity of A. Wow, blanked out there. Um, Minus the overall uh, molecular velocity. And then for our mass diffusive flux, we have our density of A uh, times the velocity of A minus the mass. The mass velocity. Excuse me, I'm kind of blanking here. Um, and so from here, um, we want to try to see what we can get rid of. So for this one, um, we know that the net um, molar flux is equal to 0 for this because it is in a contained system, and so nothing is leaving the system, and so the net molar flux for this will be 0. Thus, in the equation for molar flux is the concentration times the velocity, molar velocity, and we can therefore say that the velocity is equal to 0 because it's not possible for concentration to equal 0 because we're not in space. So we can go ahead and X that right on out. Um, so we are now left with this here. A, V, A. And then from there, we see that we have VA here, VA there, so we can then change that around and plug it on in there. So now we have our mass diffusive flux equal to the density of A times the molar diffusive flux over the concentration of A minus the velocity. Oops. And so we can further simplify this here, these two, with, let's see, rho density, excuse me, density is equal to mass over volume. And concentration is equal to moles per liter. Um, ooh, I am blanking. Moles per liter. So from there, let me clean this up. We can then cancel those two out, and we now have mass per moles, which is equal to molecular weight. So it's going to become molecular weight of A molecular diffusive flux minus the mass velocity. So, halfway there, but kind of not really. Um, we now need to see if we can change the terms of this velocity. So, how can we move this around? Velocity, we know, is equal to the sum of the densities, um, the individual densities, and the individual velocities. Yes. VI. Um, and so for this one here, we know that V is then equal to density of A times the velocity of A plus the density of B times the velocity of B over, ooh, excuse me, I'm forgetting the row, the density. I tell you, it is funny to not be using the letters. My mind wants to go to the letters. But from this, we already know what velocity is equal to, as we did over here. Um, we know the velocity of A is equal to. The velocity of B is the same. Their equation for both of them is the same because they're both doing the same thing here, and they're equal in ideal gases. So, uh, VB, velocity of B, will be the same thing just for B. So this then becomes density of A times diffusive flux of A over, what's that, concentration of A, plus density of B times diffusive flux of B over concentration of B, all over the density, total density. I keep wanting to make this a P, over total density. Um, and so when it comes to, we have a term here that we would like to get rid of. We have our, well, first of all, we'll go ahead and simplify this a little bit more. As we know, the concentration, the density over the concentration is going to equal to molecular weight yes, A. Is there anything? No. Molecular weight of A plus the molecular weight of B times over rho over density. Wow, I keep wanting to make that a P. Excuse me. And so from there, we want to see what we can do about this diffusive flux of B. So how are we going to do that? We know that in diffusive flux, when it comes to diffusive flux or diffusion overall, one particle moves in one direction and another particle comes and takes that place. So what that means for this is that the diffusive flux for JA is going to be moving over here. Diffusive flux of diffusive flux for B, diffusive flux for A is going to be moving over here, and then diffusive flux for B is going to be moving the opposite direction. So that is going to mean that diffusive flux of A is equal to the negative diffusive flux of B. Therefore, diffusive flux of B is just equal to negative diffusive flux of A. So we can go ahead and move that in there. Flux of A. Diffuse flux of B. Oop. Over density. So that equals the mass velocity here. So we're going to go ahead and plug that right on back on in. Right back on in. Wow. I forgot to fully, I didn't fully distribute that. So here we are back in there. So now we have our mass diffusive flux is equal to our molecular weight times the molar diffusive flux minus our density times, let me go ahead and copy and paste this. Let's see. Copy that. Right over there. Love technology when it works. Right there. And so for here, we're gonna go ahead and simplify this out. We know, well, mainly we know that density of A over total density is equal to mass of A over the volume divided by total mass over volume. And that's just going to equal mass of A over mass equal to molecular weight. Mass fraction. Excuse me. I was like, why did that sounded wrong? So we want to change that out here to become our mass fraction of A. And then I'm gonna pull out all those diffusive flux of A to become diffusive flux of A equals move this over. Seems like we're kind of running out of room. Diffusive flux of A equals the molecular weight of A minus the mass fraction of A times the molecular weight of A minus the molecular weight of B. Make that into this. All right. And so we're done.